what does the C look like as a function of f? Okay. Well, I'm not going to do that here. Okay. So this is the function beta squared c squared minus 1. And let's draw tangent of the c out here. And so this axis would be c. Okay.
The one that equals tangent of c, is that cap over q? Yeah.
Cap over. Okay, this is what the tangent looks like. Now this function, for really small c, is going to be really big. Right? So for small c, it's going to be start somewhere from here. Okay, when c is equal to beta, okay, this turns 0. Okay. So let's say, let me put beta here. Okay, so we just have to connect them, and regardless of the special or specific shape, okay, because the tangent also extends to infinity. The specific shape looks something like this, but it's not. Maybe it's more. Let me think. Okay. And it comes out like parabolically here, as you can see from this. So now, regardless of the shape, there are always going to be two intersections, okay? Because the tangent, they go up to infinity. Okay? So these two intersections corresponds to two bound states. Okay, so this is the case for the even solutions. Okay? Something is different about the odd solution, as you'll see shortly. Okay? Let me label this graph as even.
But the allocation where you have only one intersection.
Yeah.
So
But
you should mention that.
I'll explain that. I'll mention that later. Okay, so now the odd state. Same kind of substitution. All right. So minus q over kappa is minus 1 over kappa over q. Right? So you just plug in this kappa over q here. Okay. So that's minus 1 over the square root of beta squared minus 1. Now you multiply both up and down by the c squared, so you get equal to minus c divided by. Okay, and this is to be matched to the tangent. All right. So now, the easy way to do this is put the minus sign on the tangent so that this graph changes. Oh. There's nothing before 2 pi that's above the there is nothing above 2 pi that's below 2 pi that's positive. And then after 2 pi we get something that looks like this. so on. Now, what does this function look like? Again, at beta, it's going to blow up. Right? So if I fix beta somewhere, say let's say I fix beta here. Okay. There's going to be an there's going to be an asymptote here. Okay. And then at 0 it goes to 0. So we just connect them with some imaginary smooth curve. And we find y intersection here. But notice that depending, because this minus tangent to C, which I have drawn here, okay, it doesn't appear before 2 pi. Okay.
Why don't you label the pi values?
Right. That's right. Pi over 2. And pi would be here.
Should I label the
You should label the other one as well,
Okay.
even picture.
Okay. So now, if I place my beta here, okay, which is to say that, why did I define beta? Yeah, beta here. Just to say that V naught alpha A squared is not that big. Okay. Then there might not be an even solution because I would have something like this, and there are no intersections. Right? But that's not the case for the odd solution.
No, this is odd, this is even.
I'm sorry. There might not be an
When you
odd
put
state.
odd on the big,
Yes. Now, but there's always an even solution, as you can see from this graph. Wherever I put this beta, because it starts out from infinity and it connects to a point on here, but there's always a bound state. But there's always an even bound state for the finite symmetric potential on a square well. Okay. And now there's an important formula that you can derive based on this graph. So if I give you some, if I specify some potential well for you, okay, I'm given a effective mass of the particle, a potential dip, and the width of the well. Okay. Then by comparing this value to remember, to C is defined as QA. Right. Yeah. So by comparing to C with C is to be a multiple of pi over 2, and then beta, which is equal to square root of square root of 2m v naught a squared over h y squared. By looking at where beta is on this axis, so comparing the value of beta with these half integer multiples of pi, you can deduce how many even state or odd state there are. So given the parameters for the finite symmetric square well, you can automatically deduce how many bound states there are. Okay. If you count both even and odd, then that's the exact. If you just compare one, then you might miss one state. But this is important. This is extremely handy in solid state or semiconductor applications, where the quantum well in compound semiconductors. Okay, you might have an interface between two different materials, and then because they have different band gaps at the interface, they're going to form a well that can be approximated as a finite square well. Okay. And this gives you a quick way. The bound states in here would be of interest if you're doing LED or lasers or something like that. And this gives you a quick way to estimate how many bound states there are. Right. So this is what I wanted to say about the,
Why don't you discuss how you can change beta? What are the parameters you can just
Okay.
change beta?
so if we could just change beta, right, there are really just two parameters, B naught and A. Right? So if I have a wider well, I would have more bound states. Right? If I have a deeper well, I would have a more bound states. Right? But the important thing to remember is, no matter how shallow, as long as I have a well, there's going to be one even bound state. Okay? Now this says something about a class of potential wells. Imagine if I have some arbitrary shaped well. Okay, like this. Then it's always possible to fit in a finite square well within that well, right? It's always possible. So that the potential of this finite square well is everywhere higher or at most equal to the original well. So if I have a bound state in this well, there must be a bound state in this bigger well. Right? So that this tells you that for a class of potentials like this, there's always a bound state. Okay? No matter how small the digit is. Okay? So this is another important message. What time is it?
Yeah, 9:50.
Okay, so maybe we should, okay.
Oh, I just wanted to say, I guess if you wanted to still use the same graph on the left for the odd states, it would have been minus potential
Yeah,
Q
you
equals.
would have this going on.
Huh?
So basically, if I
No, like, yeah, no, yeah, I mean, so you still use the same, like, one that curves down that way, but then otherwise the other one you graph then would be minus cotangent for the QA.
So you can use cotangent, yeah, yeah. If you want to use this,
Yeah.
then you use cotangent. And yeah, that's what I wanted to say. So let's take a 5-minute break,
Okay.
and then afterwards we're going to go on to talk about the probability type. Are there any questions so far? No? Okay. Yeah.
Remember there is a graph about the tangent lines and there is square.
Ah, yeah, you see the
Circle something.
Right.
Right.
Yeah, you can make a circle out of this. But there are multiple ways to do this, but I like this way. Okay. I think when they teach you how to find the for waveguides, they use the circle. Okay, so to take up your question.
If you're using compound semiconductors, you should put a ratio between their effective mass.
Yeah, right. We haven't introduced effective mass. So. And effective mass actually complicates things a little bit.